Okay, so for this lecture, we're going to go over the material in the book, at least the first chapter. We're going to follow that pretty closely. Of course, there's more detail in the book than what I'm going to tell you, so it's worth reading and understanding kind of the extra details that you will be missing here. And we're going to follow the book fairly closely here and now, but we're going to start deviating quite a bit later on in the semester, and so it's worth reading the book to understand the ideas, but then what we actually do in class for the assignments is going to be fairly different from what you read in the chapter. So it's kind of worth having both in this case. Okay, so I'm going to create the cylinder. As you see in the book, I'm going to make it taller because I like a human-sized cylinder there. And just to check, I'm going to go run over to it, make sure it looks like I want it to. And what we're going to do is set it up so that this cylinder reacts to and responds to our shots. Right? So it'll turn red and do that. So I've created a folder down here called Assignment 1 where I'm going to put the assignment-specific stuff. You don't necessarily need to do that. Turn-ins will be covered later. But you can follow as you see there. Okay, so I'm going to create a new material called Target Red. And what we're going to see is that this is going to look very similar in some ways to our previous look at blueprints. However, we're now looking at material, right? And so we can still draw these data lines out. We don't really have compute lines in the same way. We really only have one compute block, and our compute block is this target red block here, which has a number of parameters that we need to set for what's known as physically based lighting or physically based rendering. You also just see it as PBR or the PBR pipeline. And this means that it's kind of a standard pipeline that includes things like the metallicness, the roughness, and emissive color that let you get some fairly physical results to the lighting. So it actually acts like physical light when it responds. We'll go into more details on this later, of course. But for now, you can just understand that what our goal here is to set as many of these properties as we can to help our material look the way we want it to. Okay, so it's going to draw from whatever lines we draw out and help us fill in those details. So in this case, of course, we just want to set a base color because we want to turn it red. And so what we'll do is create a vector parameter like so, very similar to the nodes, except in this case we're really just creating a simple node. But a vector parameter, when we're talking about materials, is a color. So it's a 4 vector where each of the, rather than x, y, z into the world coordinates, we're red, green, blue, and also the alpha color. And so we can set our red here. I could also just set the red to 1 here if I wanted to, so I could make it a pure red. You're welcome to vary this. Of course, this is not is a creative choice, so it's worth choosing what you'd like to choose for this class. There's no reason to feel obligated to stick with colors or properties. And actually, one of the really nice things about the way that all of this works is that there's plenty of room to play with all of the parameters. So all the parameters have some play, some give, and none of the numbers are ever precise in any means. So if we use 0.4 for metallic, there's no reason that you couldn't use 0.43 and decide that you like that better. So certainly feel free to start experimenting early as you go through this. Okay, so you'll notice that I did double click the box here in order to choose my color and set the color picker. And then what we're going to do next is actually fill in some of these other PBR properties to give it a different feel, right? So we're going to set our metallicness and roughness, and so I'm going to set a scalar parameter. So we did talk about this with variables before, that we have some variables that represent vector values and rotations, and some values that represent int, bool, and so on. So the way to think of scalar and vector, if you haven't heard those terms before, scalar is a single value of some kind, and a vector represents more than one value. So a vector in 3 space has 3 values in order to represent the x, y, and z position. In 2 space it only has 2 values, but a scalar always only has 1 value. It represents a single value along some dimension, like speed or distance or height or mass, and so vector values usually have like a direction associated with them. or in this case a color. So the scalar parameter we're going to use here is going to be our metalness. So let's actually change the name of our parameters too. So we've got color as one parameter and metalness as a second parameter, and we'll go ahead and set the default value to 0.5. And we'll see what kind of difference that makes. Not a lot, but what we can do is, of course, see some interesting changes as we start to change our metalness, and especially when we include roughness, right? So the metalness is kind of the hardness of the surface. Roughness is almost like a microscopic parameter that defines details we can't really see with our eyes, but the light will respond to. And so you can think of roughness of 0 means it's perfectly smooth, which means we've got kind of a mirrored surface, which you see here. And especially if our metalness is fully high and our roughness is fully low, then what we have is a perfectly mirrored surface, right? Although it's tinted red. And we see that by reflecting the world around us that we're looking at here. And you can use the scroll wheel on your mouse to zoom in and out, and of course just rotate as you normally would. So here's one case where we can start to play around with the parameters. Let's take a look at what 0 metalness looks like. And this is closer to something like a plastic surface, where it's a little softer, a little less, the light responds a little more noisily into the surface. It actually would descend partially into the surface. And this is somewhat represented by the math here. And then the roughness, if we want to set it fully high, is now it's kind of a rougher surface. Again, it's a microscopic roughness that we can't really see, but the light is responding to. And again, we'll go into the details like on this more often. But this is a good idea to kind of understand how the parameter space works on things that you're playing with, especially with materials where you get the response immediately and you can kind of see what you're looking at. You can go from 0 to 1. Almost all the parameters here go from 0 to 1, including colors. So it's 0 red or 1 red. And so you can play around with those numbers and get a sense for the two extremes. So we can also look at, actually let's look at a fully rough metal and see the difference here. Hard to tell much of a difference really between a fully rough metal and a fully smooth metal, or a fully rough plastic surface. But anyway, so let's pick 0.5 for both, just to go middle of the road, and then you're welcome to deviate from this as much as you'd like in your own example. Okay, so moving on, we're going to, just as we did before with the cube in our example, we are going to set up a blueprint for this cylinder here, and I'm going to make sure that cylinder blueprint shows up in my assignment 1 folder. So I select that and then come over here and I can see this is all very familiar at this point. We're not going to use any of these nodes. We're not going to actually use the overlap event here. We're going to use the event hit, and so that one is coming from the fact that we have a collider attached to us, the collision here, and we are going to take advantage of that instead. So you also see that there's a lot more details. So just as we talked about before, there are reference to the other pieces that we're hitting, the other actor, the other component that we're running into, a lot of information about the hit location and so on. And we'll use some of this later on, but for now, what we want to do is set the material on our static mesh component. So you'll see there's 2 set materials. Make sure you click the one for the static mesh component so that we get so we're setting it to the right place. And you'll notice it already fills in our static mesh component. So this is referencing this component here, and we're going to change the material right here in code. So we start with a basic shape material, and even if we wanted to, we could come in and change it to our target red. We could go look for that target red this way and find it, but we're going to do this in code instead, right? And so the material we're going to set it with a constant value for now. You could actually create a variable that's a material reference, so that you could set it publicly. In this case, this is an easier version, and you're welcome to sort of go more advanced as you become more advanced, right? So what we expect to happen here is that when we have an event hit, we're going to walk this line and set our material. So while we're at it, why don't we go ahead and set a breakpoint so that we can feel pretty comfortable about what's happening. So you'll see that we had a little error message there. It was because it hadn't been compiled yet, so it wasn't really ready to set a breakpoint as you might expect. Always remember you need to both kind of save and compile as you're moving through. Okay, so if all worked well, then if we shoot our gun at our target, then it should turn red, and it will stay red. And so we see that we hit the breakpoint as soon as we hit it, which is good. That's kind of the expected case there. And then we'll go ahead and resume over here, and we see that it's turned red, right? And in fact, I shot it again, and so it's red again. So let's go ahead and stop and remove that breakpoint. And now we feel pretty comfortable, at least with that change. So let's go ahead and test it one more time. Okay, so this is pretty good, and our cylinder responds the way we want it to, but unfortunately, if we run into it ourselves without shooting it, it still turns red, and so that's not really the right thing, right? So we need to add some extra code to make sure that this only turns red when we shoot it. Now you might also check and see that the cubes running into it don't change it red as well. Turns out they don't for different reasons that we'll get into with the physics system later, but for now, we're just going to work with worrying about whether or not our player person is hitting it. So what we need to take a look at is who is hitting us. And so we can start by taking a look at the first person character. We'll go ahead and look at the spawn projectile over here. So I think, let's see, our spawn projectile, yeah, so the class is first person projectile. That's what we're spawning and creating when we fire off. So again, we can trace the code here. It's the input action fire. Goes through this whole animation sequence, a montage that's going to play specific to the character, our FPS player firing off the gun. You'll see a small amount of movement when that happens. And then we spawn the projectile. So spawning is something that we'll do often because we're going to create projectiles like this in all sorts of cases, or enemies, or whatever. So it's worth understanding that, but right now what we'll worry about is that we're essentially just creating a new one of something, and in this case we're creating this first person projectile. So if I go look at that, we can see that it's a first person projectile that we're creating. This is what we're colliding with. And so in here, if we look at the other, we're going to be talking to its kind of top level object here. The component that we're actually running into is probably this collision component here. Okay, so if we ran into that, we could also look and see. But what we kind of care about is whether or not we're running into this first person projectile. So in order to check that, we can use this concept known as casting, or downcasting, where what we have here is an actor, but what we really want to know is whether or not we've got the first person projectile. And so this is kind of the first instance in the previous lecture, or in the programming lecture, we referred to the fact that we want to be able to set properties on specific classes, right? So we are our blueprint is inheriting from the actor class, and we're adding variables that are specific to our component that we might want to set from somebody else, right? The damaging or poison or whatever it is. And so in this case, we're on the class that we're being looking at, but we're going to go and figure out if we're being hit by the bullet. You could do this the other way, where the bullet itself, or the projectile, could detect the hit and then apply a property on the cylinder. So you kind of have that reflexive property, because the event hit will happen on both, and you'll have both the my component and the other component on both parties that end up getting hit. So in this case, our example, we're just going to look at the other here. We're going to cast to first person projectile. And so what this does is takes an actor as the input, right, and tries to treat it as a first person projectile. Now what's cool here is that now, given this first person projectile, if I had, say, special variables, so in this case we've got this small group of my projectile variables here, we can actually go and say, well, I want to get one of the variables on here, so get my projectile or get sphere or whatever, and these are all getting variables off of the my projectile set from over here. Okay, so we really have an instance of a first person projectile, and so we could potentially go and set its health or do something like that if we wanted to. In this case, again, we don't care. We just want to set the material because now we know it is a first person projectile. However, we have two options, right? So we have a kind of built-in branching that's happening here as well. So we have two execution paths. One is the assuming it all worked and our first-person projectile, what we were hit by was a real first-person projectile, then we get the successful cast over here and we turn red. The other case is whenever it fails, whenever we're being hit by not a first-person projectile. And so now we know that this would not be valid along this execution path. So we can do something like print string and say not a projectile, which is not going to be useful in general, but we'll use it as an example for now, just to show that we're going through the two separate paths. One case where we are a projectile and the other case where we are not. Let's go ahead and compile and save. Of course, we'll test it as we always do. I'm going to run into it, and we see that we're getting a whole lot of messages about us not being a projectile. It wants to make absolutely certain with a whole lot of messages that we are not that. And thankfully those messages go away after a while, which is great. But if we shoot it, now we do get red material getting set. So this is exactly the behavior we want in this case. So let's make our cylinder a little bit more interesting. So again, I recommend you look to the book for some added detail. I'm going to kind of walk through this pretty quickly and expect that you can go read through the chapter to understand the nuance and the detail that I'm skimming over. So what we want to do is move our block, and so we've talked about this a little bit. We're going to actually create two variables. One is a speed that we can set with a floating point value here, and another is our direction. And we'll set that with a vector because vectors are usually directions, and then scalars are usually other simpler values like mass and speed. And we'll set our default direction to be, say, y10. And we're actually going to want to normalize our direction, so we'll worry about some of the math on that later, but what that means is that we're going to make the length of direction be 1. And that way we can scale it, and we know that whenever we scale it by another vector or by another scalar, then it will be exactly that length. So what we're going to end up doing is multiplying our direction by our speed. And so when we do that, we want to make sure that we get exactly our speed back. That's kind of a property of vectors, and we'll go a little bit more into this, especially as we talk about physics, the way vectors and scalars work in those kinds of senses. For now, you can kind of just understand it as it is. And so, just as we saw before, we're going to go ahead and pull out our event tick. And this gives us a delta seconds that we can use to multiply against our speed. And recall that when we multiply a speed times a time, we get a distance, right? And so now we have a distance. What we want is a distance and a direction, right? And so we are going to multiply, actually first we're going to normalize. And the other advantage of normalizing here is that we can not really worry about the length of this vector here. We know it's a direction, we know it's going in one of these. But the reason for normalizing, again, is to make it a length of 1. And if you recall from math, whenever you multiply anything by 1, you get it back, right? And so the direction, although each of these numbers might not be 1, we might actually have something like 0.5 or well, let's say 1 and 1. I'm not going to try to do vector normalization in my head. This is going to point in a diagonal direction that we will normalize so that the length is 1, because the length is not 1 here, it's actually a length of 2. And so this helps us to just easily set our direction however we'd like. We can set it in a diagonal, we can set it forward or to the right as we're doing here, and we'll just keep it simple and move it right and left in world space. But normalizing is a convenient way to keep that size down. And again, as we multiply, let's do multiply from this side. So we're going to say vector times float. I'm going to go ahead and get an edge crossing here. I always complain about my edge crossings when I'm dealing with edges like this. And now we've got a direction and a speed given the delta seconds. Now if you aren't necessarily working with the event tick, although probably if you're using delta seconds then you are, There is another one, and I think the book does talk about this. There's the get world delta seconds, which is essentially the same value that's coming in from here. But we're just going to use this as our value and get a few extra lines in the process. And we'll go ahead and deal with that. So now we need to get our transform, because what we want to do is modify our character, right, or our cylinder. And so I'm actually going to go a little bit more detail here. Let's see, I will just put a block around this part and create a comment and say so given a direction and distance, we can now modify our transform. So let's do another block up here. And actually, while I'm at it, I'm going to go ahead and just create our comment section here and say respond to hit. Okay, so let's get our I'm just going to bring it over this way. Alright. So I think you can get it that other way, but I'm just dragging it from here. This gives us a reference to our static mesh component, and we can use this to get our world transform, our current location in the world. Now we could, I think I'll split from the book a little bit. There's a detail on dealing with its full transform. I'm just going to get the world location, and that's what we're going to modify when we add to it. So we're going to say get the world location, add vector plus vector. Actually, let's do it like this with these two lines. And then lastly, we will add that back into our world location again. So I'm going to make a copy, or I'm just going to get this guy again. This time I'm going to say set world location. Now again, you also saw that I could add a world offset. I could even just, rather than getting the world location and setting it, I could add the world offset. We'll go ahead and just do that and treat it this way pretty easily. So given that, we can now, we're calculating direction and distance, and let's just go ahead and bring all of these down here, and we'll create a second block that says to modify it. Kind of obvious. Alright. So given our direction and distance over here, we're going to modify our location by that. And let's go ahead and take a look at how that works. So what we should see is nothing. Oh, I forgot to set the mobility. So here's a detail from the book that I missed. So we have a few different settings for mobility. These are optimizations. So it is usually a good idea to leave your objects as static, because Unreal can take advantage of that and combine objects and make them more efficient when they're all static. However, we don't want all of our objects to be static, and so we'll set this one to movable because it's going to be moving all the time. I will let you go and look at the differences between these three and read the documentation so you can understand when you want to use static versus stationary versus movable. Okay, and finally, we still don't see it moving. However, I forgot to set the speed as well. So we again have two options. One we can, let me set that back to 10, just so we can look at that. One, we can set our default as we saw before, and remember we're talking centimeters, so that's about a meter per second there. I'll leave it at exactly that. But we could also make it a public variable and then set it per each cylinder. But for now, I'm going to leave it as a private or a hidden variable and just look at whether or not it's going to move. Okay, so finally we have it moving. And we'll find that although it's a reasonable speed, it also maybe it's probably not that challenging, and of course you hit it pretty easily. We also have another problem, and that is that it never stops. So it actually moves, it just keeps going out of the view. So let's take a look at how to resolve that. So the way the book does this is pretty interesting in that it uses a new kind of node which actually doesn't execute in the normal way. And so what happens is we have this delay node which essentially does nothing or doesn't execute until the delay is finished, right? So we're coming in here, we're executing every tick, and then we've got a line that comes out of here, but nothing happens on that line as long as this timer hasn't gone off. And so it's a little bit different than normal, because we normally expect these lines to constantly have flow through there, and this one actually can sort of stop us from flowing, which is kind of a cool trick, and one that might be useful to keep track of for later. So we're going to follow the book's example here and use this flip-flop node, mostly so that you have experience with it. This is I find this one a little strange way to solve this particular problem, but the flip-flop can be useful in that what happens is every time it's executed, it's either going to execute the A line or the B line. Now, depending on how often you execute that could be kind of crazy. I think it probably works really well in a pair like this, where what we're doing is setting the direction to negative and then setting the direction to positive. Now this is not the probably the best way to do this. If you want to challenge yourself and become a little bit more savvy with setting these up, what you can do instead is try to figure out how to, rather than flip-flopping, every time you come through here you can multiply the direction by -1 and then set it back to itself. And so by doing that, if you multiply something by -1 twice, it becomes itself again, right? So if you multiply it once, you get the negative, you multiply it again, it gets positive, and what you do then is flip the direction along sort of the origin, or you just mirror the direction. And it can be any direction. In this case, we're kind of fixed to only being able to move left and right, given the fact that we're changing the y value, which is reasonable, but I definitely challenge you to go in and make this a little more advanced. Take your first opportunity to kind of use a little bit more logic than what the book is providing you. And let's save, and then we will test this out and see if we do indeed stay within our lane. So we'll wait about 6 seconds and hopefully see it go the other direction. Good. Okay. So I talked for about 6 seconds there for it to flip. And this is pretty good, but of course the speed is probably not what we want. I would say we might want something on the order of 300. And let's go ahead and set the speed a little bit lower. I mean the duration a little bit lower. In fact, just so that the cylinder is moving kind of in front of us, at least in the first case, I'm going to set it right here. Let's go ahead and save. Notice that saving the scene over here does not save anything else. Again, remember to save each of your nodes, each of your scenes. I think there is a save all around here, but just keep those in mind. Yeah, so Control-Shift-Save saves all, which is a good idea. But also remember to compile and save. These things do tend to bite people with Unreal, and you lose work and all kinds of fun stuff like that. So keep that in mind. So now we've got a cylinder which is moving much more quickly. See what happens. Oh look, it can move a cube in its way, so it has no care in the world for the fact that it's running a cube.